Hello, I wanted to compile a list of the different containers in C++ and Python and show where they fit into different algorithms. So in general, most of the containers you're going to use in C++ come from the standard library, and in Python, most of them are either you don't need to import anything or they come from the collections library. And I'll go through these row by row and make some comments about each of them. So a tuple is what you use if you just have a few elements and you want to return them together from a function or move them around together and keep them together. And they can store heterogeneous elements and they're immutable, so you don't have to worry about insertion or deletion. And you should know which index each piece of data is. So I'm considering that constant search and access time. The rest of these containers store arbitrarily large amount of data. The most common one is the vector, and the vector we use an array as the underlying container. And an array looks like this on the left. You have a bunch of data contiguously in memory. You index it by integer, and that makes it very efficient to iterate through. And the vector or list classes gives you an API to add or remove elements from it. And it's useful for most general purpose containers. If you insert into it, if it's hit at the max size, it needs to copy all of the data to a new location with double the amount of space. And so in worst case, the insertion time is order n, but if you average this out over adding all of your elements to the container, most of the time you're not going to have to move the data. And so on average, it's order 1 insertion time. And search time is linear because there's no ordering to the data. The next set of containers are sets. So sets are good when you want to enforce uniqueness. So you only want to store a piece of data once, and there's some comparison operator to consider something unique. And there are two ways to do it. One is ordered and one is unordered. If you want an ordered container, then you need to have a comparison operator for your data. If it's unordered, then you're going to use a hash map instead of a binary tree, and therefore your data needs to be hashable. So in C++, this is the set class, and the unordered set is called unordered set. And it's the reverse in Python. The class that's just called set is the hash map, the unordered version, and if you specifically want order, then you need to specify ordered set. And if you have the ordered version, then your insertion and search time is logarithmic. And if it's ordered, then it's constant time, and it's just the time it takes to hash the index or the data in order to access or search it for it. And a hash map looks like this. It's a very large array, and you take your data and use some hash algorithm to get the index of where you're going to store it in that large array. So it takes a lot of memory, but you have your constant insertion and search time. In contrast, a binary tree uh, has a tree where you have to traverse it to find where your data is or to insert or delete. And there are some algorithms for balancing it so that you don't have an unbalanced binary tree. And if you have a small collection, then the binary tree, the ordered version of a set, is usually better. It's usually faster and takes less memory. But asymptotically, if you have a ton of data, then the hash map order 1 insertion and deletion time will get faster when you have a lot of data. So most of the time you're going to want the ordered version, but if you have a lot of data and you don't care about order, then the hash map could be better. And the maps are very similar, but instead of just using your data to store and access the data, you have an associative index. So you could have a string or um, some other key to access your data. And so this is good for associative containers. And similar to the set, C++, default map is the ordered version, and you have to use unordered map in order to get the hash map version, whereas Python is the reverse. OrderedDict needs to be specified, and just plain dict, the dictionary with the brackets, will use a hash map. And so your index needs to be comparable if you're using ordered, and it needs to be hashable if you're using the unordered version. And it has the same search, insertion, and deletion time as set. The last four rows on this list are different versions of linked lists. So a linked list looks like this, where you have a head node and it points to your data for that node, and then it points to the next node. So there's some overhead here because we need to create another extra object to store the pointer to the data and the pointer to the next node. And in a vanilla linked list, you just have your head and it goes in one direction. But you can also have a doubly linked list, which we'll talk about, where you have one pointer pointing to your next node and one pointer pointing to your previous node. And this lets you add or remove data from either end. And that's pretty useful. So your default list is usually inferior to your vector or deck. If you only need to access data on one end, then you can just have a vector that you append on. And because you're storing it in an array, you don't need to create this extra node object. So despite how often linked lists occur in algorithm problems, they're usually not practical to use. Insertion is always constant because you just need to create a new head node, point it to the previous head node, and then you're done. And there's you never have to copy and move all your data. And search time is linear because you have to start at your head node and then follow the pointers until you get to the data you want. In contrast, double-ended queue allows you to access data at either end. So you can add or remove data from your head or your tail. And this makes it more useful to do something like a queue. And this is also the underlying container for a stack or a queue. So your deck, stack, and queue in C++ are templated, and you can change the underlying container. But by default, they use the double-ended queue. And a double-ended queue can do anything a stack or queue can do, but the stack and queue classes in C++ just give you the API to restrict the stack so that you can only push and pop from the top, and for the queue you can only add to the back and remove to the front. So it's more of a convenience that restricts you so that you avoid errors. In contrast, Python just has the deck class in the collections, and you can use that for doing anything that the stack and queue can do, and you can uh, you can add or delete from either end. So because this uses the linked list type of structure, insertion or deletion time is always constant, and you would never search through these because you're using this data structure because you only care about what's at the end. So that's the stack is useful if you're doing something like depth first search, because if you're at a certain place in your tree or your graph or wherever, you want to add on the current node and then add on your children, process the children, and then you would pop them off the stack, come back to your parent node, and then do the processing of the parent after the children. Whereas in a queue, you can use this for scheduling. So if you add in a job, you want to process the ones you added in first before you get to the ones that are at the end. But it's also useful for breadth first search, because in breadth first search, if you're at a node, you want to process that node and then process all the children. So you can add all of the children to the end of the queue, and then you'll process the parent from the front of the queue first before you get to the children. So that is a very brief overview of the different classes you would use in C++ and Python for these different containers. And these complexity times should help with figuring out what the complexity is of your overall algorithm by knowing how much time you're spending adding or deleting or searching through your container.